Hello, Health Science 3052. Yes, this is the second video. This is for Thursday, September 3rd. And again, I'm going to try and keep these as short as possible for you because I really want you to focus on the PowerPoints. I want you to read them and I want you to generate questions and ask those questions to me. So I'm going to give you a cursory information on the video slides themselves, I should say the PowerPoint slides, and then we'll go through this material um, fairly quickly, but at the same time give you kind of all the highlights that you really need to know. Now again, with regard to your exam, the materials are going to come right off the PowerPoint slides. Okay, so you don't need to fish around and try to find the answers online. If you go online and you find answers, they may be wrong. If you pull your answers from the PowerPoint slides, you can guarantee that they're going to be right because I test from my PowerPoints. Okay, so with that, we'll go on to population dynamics. This is for Thursday, September 3rd. So population attributes are measurable characteristics that are unique to such groups, such as the birth rate, the death rate, age structure, population density, spatial distribution, things of that nature. So when we talk about the population, like say for instance, the human population in San Bernardino is going to have specific characteristics. The birth rate is going to be unique. The death rate is going to be unique, especially, I mean, even if you're comparing San Bernardino to Loma Linda, these population attributes will be markedly different. You will definitely see some variability between those two areas. On to slide 3, biotic potential. Biotic potential is the maximum growth a population can achieve in an unlimited environment. So biotic potential is really kind of a modeling piece. If we had unlimited environmental resources, how much could our population grow? Obviously, there are environmental factors that never allow this to occur, but biotic potential is certainly something that is unique in the ability to make calculations based on species growth over a given period in time. So if there is unlimited resources for a short period, what effect will that have on that population? And certainly with human growth being on an exponential growth curve, you really kind of wonder how close we've come essentially to that biotic potential. Environmental resistance, again, this is on slide 3. There are going to be limiting factors such as predation, disease, overcrowding, food shortages, water, things of that nature. So you've already heard me talk a little bit about environmental resistance and how that's going to affect the population of a species in any given area. And we certainly wonder very much about how environmental resistance can potentially affect humankind. And we kind of wonder, you know, food shortages, disease, obviously, with coronavirus. You start to look at these numbers and start to kind of develop some different thoughts on these things. So biotic potential minus environmental resistance is going to equal the actual population growth. A fairly interesting idea in that you can derive a mathematical formula that comes right out of, you know, third grade math that says that your biotic potential minus environmental resistance will equal actual population growth. And you really see that with certainly with humankind, that as environmental resistance has fallen off for us, we're getting a lot closer from biotic potential and actual growth of population. So interesting stuff. So on to slide 4. Slide 4, the population curves. So you remember there's a S curve and there's a J curve. Homeostatic control, self-regulating controls, behavioral, physiological, and social responses within the population are going to have effects on these growth curves. Right now, currently, human population consistently is growing in a geometric fashion, and we'll talk a little bit about that. The problem really comes in, as you see with the last part of that slide, is that the agricultural production grows arithmetically. So think of addition and subtraction, where the human growth population is multiply, multiply, multiply. So currently, the human population, if we go back to the J and S curve, actually let's jump up to the next slide. On slide 5, there's a good representation of this. So currently we're on an unrestricted J curve of human growth, which is exponential, and you'll see that in a couple slides coming up here, that we are growing at an exponential rate, and it's consistently doubling at a much faster rate, and that's that exponential growth. Now, eventually, the theory is that we're going to hit what you can look at on the right side of the slide, which is going to be the point of maximum growth. And then at that point, what's going to happen is it's going to begin to plateau and slow down and form that S curve. And you're going to be able to really do some basic calculations that are going to show that environmental pressure is going to be the reason that we're going to start seeing that flattening out of the J curve into the S curve. And it could be that we run out of food, it could be we run out of water, it could be that we fight off coronavirus. Any number of these things could have an impact as to why the J curve of human growth population ends up becoming an S curve that you see on portion B of this slide. This is really important, and I really want you to kind of focus on this and give that some consideration, because there are a lot of different environmental factors that cause a species to slow down and how fast it is striving towards that biotic potential. And generally, they're not good things. Shortage of water, shortage of food, space, all these different components that allow for a species to continue to grow in an exponential fashion, and then it will flatten out to that S curve, which is essentially going to be environmental pressure bearing fruit on that specific species. So that's slide 5. On to slide 6, we have the historical population trends over time. And if you look at this, I mean, we start back at 8,000 BC. We go from essentially BC, where it switches over to the Common Era. There were about 0.2 billion people on the entire planet. Excuse me. And then in 1650, you see the doubling from that to 0.5. So from 0 to 1650, you have a doubling. And then from 1650 to 1850, you have another doubling where you have 1 billion people on the planet. And that was in 200 years. And then from 1850 to 1930, which is 80 years, you double the population again. So you can look at these. 75, which is 45 years, another doubling. And then you add 1 billion people from 75 to the late 80s, and that's in 15 years. And then another billion added to that from the 80s until 2000, which was a 10-year period. So you see how the population is continuing on that J curve of human growth, population growth, which is just explosive. Will it flatten out to that S curve? It's hard to tell. And certainly, when you consider the human population and its growth, I mean, it's been consistent over time that it's just speeding up. A lot of people have tried to generate theories on the carrying capacity of planet Earth for humankind. And because of our scientific advancements, it's really hard to tell where that lies. And you'll get varying degrees on that answer. So some people say we've already met and reached our carrying capacity, which is why we're seeing things like coronavirus. And other people will say that we haven't even come close yet, that essentially the world, the carrying capacity for humankind may be closer to 1 trillion people. I seriously doubt that is the case, but who knows? Science is a fascinating mechanism with humankind, that we are able to employ this and really have some phenomenal results. So who knows? There are some very interesting things like changes in the food supply that we have, where we have crops that grow extraordinary sizes of things like corn. So my mom's a soybean farmer in Iowa, and she's shown me ears of corn that are being grown today, which are about the size of, almost literally the size of my forearm, where if you went back to when the first settlers landed on Plymouth Rock, the corn that they were sharing with the Native Americans was closer to the size of my hand. So you can see the difference. It's fairly extraordinary in regard to what we've done with genetic modification. Am I a fan of genetic modification? Um, it depends on the day, I'll be honest with you, and it depends on what I'm eating. But certainly there are a lot of unusual and very complex things that we're going to be talking about in regard to how we move forward with humankind. Some of the lectures, like next week, we're going to be talking about the food supply, and certainly without genetic modification, we wouldn't have even come close to being able to feed the number of people that we're feeding today. Is it a good thing? Is it a bad thing? Could it lead to our own demise? Who's to say? How much does it have to bear in regard to what's taking place with colony collapse disorder with the bees? And as you know, without the bees, it's going to be really hard for us to get food. So interesting times. A lot of ethical questions that no one really has a solid answer on. So that's slide 6. Slide 7 is a discussion of the birth rate. The birth rate is the number of babies born per 1,000 people per year. And it's very easy to look at this figure and be able to compare birth rates in specific areas. And we'll talk about this a little bit when we talk about age structure when we get to kind of the last slide here on slide 13. So with birth rate, very fascinating stuff, because as when we generate a population that is almost unsustainable, the birth rate is usually going to be affected. And certainly is one of those things that can be a challenge. Affecting the birth rate, it takes some very ethical considerations and begins to put them in play. And we'll talk about those as the lecture progresses. But the birth rate is an easy figure to take a look at. Pre-industrial revolution, the rate was 40 to 50 in most societies. These days, the range is widening substantially. So again, Spain with 10 being the lowest, number of babies born per 1,000 people per year, with Spain at the lowest. And then you have Niger, which is at 53, which is the highest currently. This information is a little bit behind. Certainly you've seen some interesting things over the last couple of years, where Germany has actually incentivized its people to continue to have children. And certainly very interesting stuff. How do you affect the birth rate in a place like Niger? And we're going to discuss some of the complexities therein and why that's such a challenge, and I think that's in the next lecture. So death rate, number of deaths per 1,000 people per year, and this is going to be considered as a crude death rate, so it doesn't account for variations in age. So the death rate can be higher in predominantly older than it is with the younger populations. So if you have an area that has a large senior population, you may see the death rate is actually affected by this. So I live in Laguna Hills, right next to Laguna Woods, which is a massive senior population, and certainly the death rate can be affected by that. Does it affect the whole of the death rate in Southern California or the United States? Most certainly not. But when you're looking at specific figures, these death rates can be impacted by the fact that you have areas that are conglomerates of different age populations. And certainly with Loma Linda, you see this, that the death rate is actually much lower because you have people that are very active and very focused on diet and things of that nature. So you can see the death rate being affected by this. But this is the number of deaths per 1,000 people per year. So different from the birth rate as the number of births. So it's pretty straightforward, right? Births is the number of births. Deaths is the number of deaths per 1,000 people per year. And these figures can be very useful from a public health standpoint, and these will be something that you'll start looking at when you take your MPH here at Cal State San Bernardino, which I advise you to do. What an extraordinary program it is. On to slide 9. Total fertility rate. Total fertility rate represents the average number of children a woman would potentially have were she to fast forward through all her childbearing years in a 1-year period. So in a single year, under age-specific fertility rates for that year alone. So total fertility rate is kind of interesting because it's going to look at, this aggregation of information. So this one individual, their total fertility rate is based on how many kids they would have throughout their childbearing years, taking in factors in those specific areas. So it doesn't include birth rate or death rate. It's really looking at the total fertility rate of reproductives in a given area. And slide 10 is a map of the total fertility rate, and there's a really good reason why the total fertility rate is so high in sub-Saharan Africa, and we'll definitely talk a lot more about that, why that is. That's slide 10. On to slide 11, again with total fertility rate, we're looking at Yemen being 7.6 and Hong Kong being 1.2. And again, this is an estimation of how many kids a woman is going to deliver in her total of her reproductive years, which, as you can see, has a very wide range, which is expressed as a percentage. So birth rate minus death rate is going to equal the growth rate, and then they change that to a percentage, and this does not include immigration or emigration, so people coming and going. So it's very important when you look at total fertility rate, why is it that people in Yemen are having so many children versus Hong Kong having so few? And this really does have a lot of ramifications in regard to public health. So on to slide 12, demographic transition. I don't really talk much about this. So if you have a high birth rate and a low death rate, that's incomplete demographic transition. In developing countries, the death rate was very high due to malaria, and down to 22 post DDT, and then it dropped down to 6. Incomplete demographic transition, so you're going to have a high birth rate and a low death rate. So you're going to start to see this demographic transition that is occurring because of the fact that there are a lot of people being born, but in addition to that, a lot of people are living longer. So there's an incomplete demographic transition, where a complete demographic transition is going to be a low birth rate and a low death rate. And this is essentially going to be changing the tapestry of the human population in regard to its age structure. So you're going to start to see people living much longer, and you're going to start to see a lot more people being born, and this is that complete demographic transition process. So with a demographic transition that's complete, there's a lot of economic liability. You start to see some challenges in regard to feeding and clothing this growing population. So we are very close to a complete demographic transition, where we have a fairly low birth rate and a fairly low death rate. And this process is going to be where you're really going to see a much more aging age structure, and I'm going to show this is going to make more sense when I show you the last slide in regard to a complete demographic transition, because we don't need to have a lot of kids to make sure that they survive. So the death rate remains low, and we don't have to have 10 kids in the hopes that 1 or 2 of them are going to survive. That's kind of the ugly side of complete demographic transition, and that's I guess that can be viewed as a good thing, but certainly with an incomplete demographic transition with a high birth rate and a low death rate, these are things that you start to look at them and go, okay, from a public health standpoint, what do we need to do? And like, say, for instance, with an incomplete demographic transition, you're going to be focused on infant mortality, infant morbidity, and really focusing on those things to make sure that this high birth rate is accommodated. Whereas with the complete demographic transition with a low birth rate and a low death rate, you start to look at other things like, wow, people are living a long time. We all of a sudden we need to start focusing on heart disease and cancer and things of that nature. So on to slide 13, the last slide. This is the age structure. So you look at age structure in regard to sub-Saharan Africa on the left and Western Europe on the right, and you'll notice a few things. And again, as I had mentioned with demographic transition, sub-Saharan Africa is not a true incomplete demographic transition, because you still have a fairly high death rate. So that's one of the reasons that you have this age structure, okay? With sub-Saharan Africa, what you're looking at is high infant mortality. Look at how many kids are being born and how quickly they fall away. Very, very few people are going to live to be 75 years old. So we're focusing on other things here. If most of the people are dying off by the time they hit 55, from a public health standpoint, you're really not focusing on cancer. You're not focusing on heart disease. You're focusing on mosquito-borne illnesses like malaria. You're focusing on nutritional deficiencies. You're focusing on things that are taking these lives at a much earlier age. Why are so many infants dying before their 5th birthday? These are the things that you would be looking at from a public health standpoint in regards to sub-Saharan Africa. With Western Europe, you look at the age structure where people are hitting 55 in very large numbers and very slowly tapering off up to 75 years old, and more people are living to be 80, and certainly more people are living to be centenarians in Western Europe. And you start to look at different things. From a public health standpoint, you begin to say, okay, I don't have to worry about these people dying from malaria. I don't have to worry about them dying as infants between the age of 0 and 5. So, neonatal care kind of gets, marginalized a little bit because we're going to be focusing on heart disease and cancer and stroke and things of that nature that are going to be affecting people when they hit 55. So the age structure is really important, and a lot of you are going to be working in hospital-based organizations in the future. You should really consider this. This is very important for you. Reason being, depending on where you work, it is going to have a dramatic impact on the work that you're doing. How do you staff a hospital in Palm Springs? How do you staff a hospital in sub-Saharan Africa? How do you look at what you're going to be doing? What is the focus of even the supplies you purchase for your hospital-based organization? What are you going to need if you're running a clinic in sub-Saharan Africa? Probably a lot of anti-malarials if you can get your hands on them, but you're definitely going to need a lot of neonatal care. You're going to need prenatal vitamins, things of that nature, to try and give these children the best leg up possible so that they can make it to their 5th birthday. Whereas with Western Europe, which is very similar to the United States, you're going to be focusing on different things. You're going to be telling people you need to eat healthy, you need to exercise, because when you're 55, you don't want to have a heart attack. It's a horrible way to live and die. These are the differences. These are the things you start looking at. And from a public health perspective, you need to consider these things. What's the birth rate in this given area? And who is having children? Do I need to start educating kids that are 13, 14, 15 years old? Or do I need to focus on 18-year-olds? Where is that birth rate coming from? Where is it being generated from? And same thing with the death rate. How many people are dying per 1,000? And what is it that's killing them? These will sculpt public health for the future, and certainly will be a big part of what you are doing throughout the remainder of your professional career. So with that, I'm going to go ahead and sign off for the population dynamics PowerPoint. And again, this is the 13th slide. So make sure that you watch the video, make sure that you read the PowerPoints and that you understand them. If you don't understand them, let me know. I really love your questions. I love getting to interact with you and look forward to all your questions in the future. So keep that in mind. Keep your eye on the announcements. Keep following the class, and you'll have great success in this course. I can almost guarantee it. People get very high scores in this class traditionally because I don't make it exceedingly challenging for you to do well. If you do the work, you will get a good grade. I don't make it a mystery. I don't hide things from you. I want you to do very well in this course. So ask me your questions. Make sure you're ready for that presentation, and make sure you're ready for your paper. Your paper's not long, but make sure it's good. Make sure it's something you're proud of. And with regard to your presentation, I wish I could do them in class because it's very important to me. But at the same time, I want to see your creativity. So do something with regard to your presentation that is different. do something that maybe you haven't done before. And definitely enjoy the process. There are very few classes like this one. You're not going to be doing math. You're not going to be memorizing many dates. But I can tell you this, you're going to get a lot out of the material. And if you followed along tonight, you're probably starting to think about this stuff and saying, wow, I never really, from a public health perspective, I never gave it much thought that the age structure, the birth rate, the death rate, total fertility rate are going to have massive ramifications on what I'm actually going to be doing in any given area. And I encourage you to explore your lives. If you get a chance to go to other parts of the world and practice your craft, which is probably going to be public health, you're going to see some amazing things. And I want that for each and every one of my students. Not just success, but a rich life of experience. And that's really what this is all about. So keep that in mind. Enjoy this class. Ask me your questions. And consider the fact that you're going through something that is unprecedented in modern history. I know this has been tough. It's been tough on all of us. I miss teaching with my students in front of me. I miss seeing your faces. I miss interacting with you. And I know it's been tough, but you've all come through this with remarkable resilience. And certainly when someone asks you, what was one of the most interesting things you experienced in your life, this will be one of those memories, and certainly has been a real challenge for everybody. But you're coming through it, and I know you'll have great success in your lives because of it. So with that, put a lot into my class. You're going to get a lot out of it. You put a decent amount of work in, and I can promise you're going to get an A in this course. So keep that in mind. Enjoy the class, and I look forward to your questions. So we will post these 2 videos. You'll have the Tuesday and the Thursday video, and then we will chat over the week, and I will